All right, Algebra 2 students, here is your lesson for today. I'm going to go through the notes on the screen. You're going to take the notes on your note page, and then I will get you started on the assignment. So our topic today is exponential growth and decay functions. Exponential growth, we see exponential growth here, right? This would be exponential decay, right? So growth goes up, decay comes down. So an exponential growth function has this form right here, y equals a times b to the x power. Okay, so a can't be 0 because multiplying anything by 0 gives us 0. B is a positive, right? That base that goes with the exponent is a positive real number besides 1, because if it's 1, it doesn't really matter what's going to happen with the exponent. So if our growth, if our factor out here is greater than 1 or 0 and greater than 1. So if this number right here is greater than 1, then it is an exponential growth factor. That means you will get something that is growing. Okay. And then B is called the growth factor. Okay. If A is greater than 0, but B, this term, then if this B is between 0 and 1, so it can't be 0 and it can't be 1, but it's some decimal in between, then this is going to be called, this is going to be an exponential decay function. Okay, exponential decay function. And then this B value is called the decay factor. And I misspoke here. This should be an exponential growth function up here in our first part of the note. So if we have a B times A, we look at that A, and if A is between 0 and 1, it's decay. If B is greater than 1, then we have growth. Okay, so here we have a growth function. That means that our B value is greater than 1. And looking at domain and range, the domain is going to be all real numbers from positive and negative infinity all the way up to positive infinity. Okay, so it extends it forever this way, and then our function is going to continue forever up. So our range is all real numbers, or negative infinity to positive infinity. Looking at range, we have that asymptote again. It is going to approach y equals 0 right here, but it's never going to actually get there. So our range is going to be anything greater than 0, right? Because it's never going to reach 0, and then it's going to go up forever. Okay, on our decay function here, we see range going from positive infinity coming all the way down almost to 0. So our range is going to be the same. It's going to be y has to be greater than 0 because we have that asymptote here. And then our domain is still all real numbers because it will go from negative infinity to positive infinity. And so when we graph these, we're going to make this very simple, right? We have y equals 2 to the x. So we're going to plug that into our graphing calculator. We're going to put the 2 in parentheses, and then our caret, and then we're going to put x as the exponent, and we're going to put both sides in parentheses just because that's a good habit for us to get into. And then we can hit graph. We see a picture, and as usual, we're going to go to table, and we're going to put in the values from our table in our note page. Over 0 up 1, over 1 up 2, over 2 up 4, and then we're going to do our best to graph that. over 1 up a half, over 1 up 1, or over 0 up 1, over 1 up 2, over 2 up 4, and then we're going to sketch in our exponential growth function, right? It's growing. Okay. Here we have, we're going to have a number that is less than 1, greater than 0, but less than 1. So we can predict then that we will have a decay function. So I have 1/2 to the x power. I get that plugged into my calculator. Okay. 1/2 to the x power. And again, I can graph it. Hopefully it comes down in decay. It does. And again, I'm going to go to table. I'm going to write in my values on my table provided. So -2 up 4, -1 up 2, over 0 up 1, over 1 up 0.5. And then I can come over here and I can graph that on my grid. So -2 up 4, -1 up 2, over 0 up 1. Okay. And remember, we have the asymptote there. It's going to approach 0, but never actually reach. So growth and decay does have a decent amount of real life application. Here is exponential growth model, exponential decay model. So the value of a car is Y, and that is in thousands of dollars, can be determined by the model Y equals 25 times 0.85 to the T power, where T is the number of years since the car was purchased. So first we need to determine if that was exponential growth or exponential decay. And we're going to look at this value right here. Okay, 25 is the initial value of the car. 25, it's in thousands. And then our factor here is 0.85. So that is less than 1. So we are going to have a exponential decay situation, okay, for this. And that makes sense, especially in cars. We've talked before about how they decrease in value over time, typically. And then it tells us to identify the annual percentage increase or decrease in the value of the car. And that's going to come right here in this part that we are taking to the exponential, to the exponent power. So we have 0.85. So we took 1 minus a rate of decay. So our rate of decay here in this problem is going to be 1 minus 0.85. Okay, so our rate of decay is 0.15 or 15%. So our car decreases in value approximately 15% each year. And then we need to estimate when the value of the car will be $8,000. So we can do various math to figure this out, but what we are ultimately doing is solving 8 for 8,000 equals 25, our initial value, times the 0.85, meaning every year the car retains 85% of its value to the T power. So the best way to do that would be to come right back into our calculator. I would say I would do 25 times the 0.85 to the x power. So I enter that in, and then 8 in my other, my y2. So then I'm going to get a graph that shows, so that curved one here in the corner is the value of the car. It started up off the screen way up at 25. This goes from 0 to 10. And then this horizontal line is the $8,000. So I would go to calc and then 5 for intersect, right? And it's going to ask first curve, I'm on Y1. Second curve, I'm on Y2. Tells me to guess. I can get it somewhat close. And so my exact T value is 7.011 and so forth. So it asked me to estimate. So I would say that those two, that our T is about or estimated at 7 years. Okay, so I use the intersect function on my calculator. You could go to table, right? And we see the $8,000 in Y2, the value of the car decreasing, right? At 0 years, it's 25,000. And so right here at exactly 7 years, our car is worth $8,014.40. So we could see here it is also there, but at about 7. So that is exponential decay. Example 3, in 2015, the world population was about 7.38 billion. During the next 5 years, the world population increased at about 1.09% each year. Write an exponential model that represents the population Y in billions of dollars, T years after 2015. So we're going to say Y equals, and then our initial value is the 7.38, and that's in billions. And then 1.09%. Well, 1.09% looks like that as a decimal, and it's growth. So it's 1 plus that rate. So I'm going to just add a 1 out in front of this, 1.0109, and that is to the T power. So then we are asked in the second part of this is to estimate the world population in 2020. So to do that, we have to figure out our T value. Our T value is not 2020 because this initial value is in 2015. So 2020 is 5 years after 2015. So 2015 plus 5 years is going to give us the 2020. So I'm going to copy down that same equation that I just came up with, right? Initial value, a growth, exponential growth factor of 1.0109. And then our T value is going to be 5 because it's 5 years after that initial 2015. Now for this one, I would just enter it into the main screen on the calculator, right? So I would do 7.38 times 1.0109, and that is to the 5th power, right? Because we know what our X value is, or in this place we're going to say T value is 5. So then I would hit enter, and I would get an approximate world population of 7.79 billion people. Okay, I went with 2 decimal places because that is what they went to here in our problem. They had 2 decimal places. Last example is compound interest. Similar to the exponential growth, and hopefully when you get a little older and hopefully start saving some money, you will also have some good exponential growth in your bank accounts. So compound interest is paid on an initial investment called the principal and on previously earned interest. Interest earned is often expressed as an annual percent, but the interest rate is compounded more than once a year. So the exponential growth model is Y equals A times 1 plus R to the T. We have to modify that for banking purposes because banks usually compound that interest. That means they pay you the interest each month. So here is our compound interest formula. The amount that you would have in your account equals your principal, your initial payment, times your rate, your interest rate that they promise you, divided by the number of months. And then that's 1 plus that in parentheses to the N times T. Now, N is, again, the number of times per year that they're going to pay out your interest, and T is the number of years. So most cases, banks compound monthly, so your end value would be 12 for both of these situations. So here in our example, we deposit $9,000. That's our P, our principal, and account pays 1.46% in annual interest. Find the balance after 3 years. So our amount in the account is 9,000 times 1 plus, because this is a growth situation, our interest rate of 0.0146 divided by, here they say it's compounded quarterly. Those things are compounded monthly, but that's okay. Divided by 4. And then we take that to the 4, because it's compounded quarterly, means 4 times per year, times the 3 years. So that means you're going to get 12 interest payments into your account each over that 3-year period. So let's say 9,000 times, and then if I plug this into my calculator, 0.0146 divided by 4, and then I add the 1 to it, I would get 1.00365. Okay. And then that would be to the 12th power, right? 4 times 3 is 12. So all this work I would be doing on the calculator, I would do this on the calculator, and then I would do this whole problem on the calculator. I would probably not do it all in one line. I would probably work on the parentheses part first. I would probably figure out that 0.0146 divided by 4. That's my quarterly rate that they're going to pay me. So I took the annual rate divided by 4 for 4 quarters, and then I'm going to add the 1 to it, 1.0365. Okay, now I'm right here. I'm going to follow order of operations. Next thing would be exponents. So I'm going to take that to the 12th power. And then I'm going to multiply by 9,000. So after 3 years, you would have $9,402.21 in your account. Okay, so that's just a quick look on best strategy for entering that into your calculator. For your assignment, you have 4 graphing problems. Okay, let's go with having you complete 1, 2, and 3. Okay, enter into y equals, fill in your chart. Okay, graph your data. Do that 3 times. Domain is almost always going to be all real numbers, and your range is going to, you're going to look and see where is that asymptote. Your graph is going to come down and flatten or go up, right? It's going to have a flat spot on one side. So that'll kind of tell you where your asymptote is. So your range might be y is greater than 0. That's what we saw in our examples. Typically, that's going to be what your range is. Down here on number 4 that you're not going to do, our whole graph is shifted down 8. So your asymptote there would actually be -8. But I believe on these 3 that I'm having you do, you would have all your range is all going to be y is greater than 0. On the back side, let's work on 5 and 6. Try 5 and 6. Use your notes, right? Number of bacteria in thousands can be modeled by this, okay? Function. Is that exponential growth or decay? Look at this value right here. There's your initial times this factor. It's going to be a growth factor because it's greater than 1, okay? So our bacteria is growing, and then identify percent increase, try and figure out when the bacteria will reach 1 million. And then down here, we have a deposit, annual interest, find the balance, 5 years, if it's compounded daily. If you can get compounded daily, good for you. So your end value here is going to be 365. So in your, look at your notes and find that compound interest formula. So work on 1 through 3 on the front, 5 and 6 on the back. We will go over this in class. Hopefully I will be back tomorrow on Tuesday. Do work.